Hey, what's up, guys? So we're gonna do LeetCode 79 word search. So all they do is they give us a board filled with letters and or a matrix filled with letters, and they give us some word, and they just want us to return. They want us to return true if the word exists in the matrix or not, and or return false if it doesn't, right? So this is pretty straightforward. We're just gonna depth first search, starting from every cell in the matrix, looking for our word. Before we get to that, before we get to the depth first search, there's some quick checks we can do to check if the board if it's even possible for the board to contain our word. So for example, we could check if the number of rows times the number of columns, so board 0.length, uh, is less than our word.length. So if there's not even enough letters to cover a number of letters in the word, then just return false. And what we can also do is check the number of occurrences of the number of letters in the board to see if there's enough occurrences in our word. So in this case, we'll just call it occurrence equals new int, and we're going to say 128 because there could be lowercase. So in the constraints, it says there could be lowercase and uppercase letters in the board. So I'm just going to do 128. We could do like 52 for lowercase and uppercase letters, but then we'd have to do some like ASCII math or whatever. But like the index minus like the letter A or something. But who wants to do that? We're just going to do 128 to cover the entire ASCII range. This is still constant space, right? Because constant number 128 is a constant. Cool. So let's loop through our board. Cool. So why did it not type a J there? J. Cool. And we need to increment the number of occurrences at that index. So our index is just going to be ij. So this is some letter. This is returning some letter, right? And we're just incrementing that letter or the number of occurrences of that letter. And now what we're going to do is we're going to loop through our word.length. My computer's lagging a little bit because of the recording and it's kind of overheating. But anyway, we're just going to loop through our word and then subtract our occurrences. So word.char at I. Cool. And if this ever hits less than 0, that means there's not enough occurrences of that letter too. And if there's not enough occurrences if there's not enough of that letter in our board, then we're going to return false because it's impossible to find that word in our board. And now we can start the DFS. So I'm actually going to copy and paste this right here because we're just going to look through our matrix all over again. What we're going to say is if the DFS returns true, then return true. And if it doesn't, if it never returns true, because from every starting point, we're going to return false. And so let's pass in, what are we passing in here? We're going to pass in our board. We're going to pass in the word. We're going to pass in the index into the word. So like this will start, actually this should be 0. So this represents the first letter of this word, and then DFS is going to recursively check index 1, index 2, index 3, and now we're going to pass in the row and the column of the cell that we're currently at. So in the beginning, so we're just starting our DFS from every cell on the board, looking for our word. Okay, so now we can go ahead and write the DFS. So it's just your private boolean DFS. I'm like trying to beat the lag on my computer. Okay, let's copy and paste these parameters here because they're the exact same. The board, the word, and this is going to be the index. So this int I is the index into this word. And we need to pass in the row and the column. Okay. And let's do some, so if we've reached the end of our word, then we can just return true because that means we've matched, we're only incrementing this I if we've matched the letters in the word. And if we've matched every letter, so if I equals word.length, go ahead and return true. And we also need to make sure that we're still in bounds when we're DFSing. So we need to check the row and column here. So we're going to check if the row or column is out of bounds. So if row is less than 0 or the column is less than 0, or if the row is greater or equal to board.length, or the column is greater or equal to board.length, then, or not board.length, this would be board row.length or board 0.length. That would work fine too. Then we're going to return false. Okay. What's next? So now let's grab the letter out of our word. So word.char at I, and we're going to check if this board matches our letter, or if the cell in our board matches our letter. So if the board row column equals the letter, or sorry, if it doesn't equal the letter, so if it doesn't equal the letter, we can just return false. Cool. So we don't want to keep going down this path if we have a mismatch. So and now what we need to do is we need to mark this cell as visited, because we don't want to revisit this cell now that we've matched against it. Like if we match against a cell, we want to say that we visited it along this path so that as we're DFSing, our DFS doesn't come back around to our cell again. So let's change this. So we're going to just reuse the board itself, and we're just going to override it with some random letters or some random character that's not a letter. So I'm just going to use stars. You could use a money sign if you wanted to. I'm going to use a star because I like stars. All right. So now we can continue our DFS. So this, because we got past this check, this means that the letter must match our board if we got this far, right? So we're going to store the result of our other DFS calls, which are just going to go in the up, down, left, right directions. We're going to try all possible directions and keep trying to match against our letter. So we're just going to do DFS board word. And then we're going to do I+1 because we want to try matching against the next letter in our word. And we're going to try, we could do row +1 here and then column. So in this case, this would be going down in our board. And then we also want to check the other 3 directions. So let me just copy paste this so we don't have to type that all over again. Get rid of that. Let's fix the spacing. Cool. And now we just got to change this to all 4 directions. So this would be call +1. We'll get rid of this. And this will be call -1. Cool. So now we're going in all 4 directions for our DFS. And now what we want to do is, once we've gone through all these paths, before we return, we need to restore this visited cell, because there are other paths that will go through the cell. Just like we marked it as visited for this path, but once we return from this path, we want other paths to be able to go through this cell, or alternate paths to be able to go through it. We just marked it as visited so that this path that we're continuing on doesn't recheck this cell. Okay, so we're going to restore this. Board row column equals the letter, because we note, so this, because we got past this point, that means that board row call used to equal this letter, and we changed it to a star, and now we're just restoring it here. And now we just return the result from the DFS calls. Okay, cool. Are we done? I think we're done. Let's run it. Cannot find symbol. What am I missing? The board. Oh, word.length. Where is that? I didn't need to use parentheses here. That's a method call. Cool. Let's run it. So we ran it. Submit it. Does it work? Yeah, it works. Cool. And it beats 99% in terms of time. And I think it's just because of these little quick, like, validation checks, I guess, if you want to call it that, where we just check that the board can contain our word. So let's explain the time complexity really quick. So this looks like it's 4 DFS calls. I mean, it is 4 DFS. It's 4 recursion calls, right? But one of these, at least one of these, is guaranteed to be O of 1, because one of these is going to retry the cell that we just visited. So, for example, like, it's going to go in all 4 directions, but then when it comes back, like, basically one of these is going to check this cell eventually. I'm trying to word this in the proper way. Like, we'll go in all 4 directions, but then when one of those tries to recur, so basically at every point, one of those is going to check the revisited, or the cell that we already visited. So what this actually ends up being is, like, if you assume that one of these is O of 1, which one of them should be, like, for the first call, so for the first method call, all 4 will go in different directions. But after the first call, after the first recursion step, then only 3 of these will actually be going in different directions, while one of these will be some O of 1 call that will just return false at this point here, because we marked it as visited. So anyway, if one of these is O of 1, and let me write this somewhere over here. So like, let's just say this one was O of 1, right? And the other 3, well, the other 3 are going to be O of, what would it be? O of 3 to the L, where L here is the length of the word. Because in the worst case, we're going to go through, you could say this is upper bounded by the length of the word, right? Or I guess it would be like, O of 3 to the L minus 1, but this comes, if on the, that just estimates out to O of 3 to the L. So the rest of these would be O of 3 to the L. So it'd be like O of 3 to the L here, O of 3 to the L here, O of 3 to the L here. So what we end up having is this whole thing is just O of 3 to the L. And if this whole thing is O of 3 to the L, this DFS call, if we call it, how many times are we calling this? We're calling this O of, you could say this is, let's just say it's O of n, because we're going through the entire board, where n is the number of cells in the board. So this whole thing would be O of n times 3 to the L. And like, if you're having trouble understanding this, like, think of this as, so these four DFS calls, we agree that one of these is going to check a cell it's already visited. But the other 3, you could think of this as like at every node in a tree, we're making 3 decisions. And then in those children nodes, we're also making 3 decisions. So like in a binary search tree, when you're going through all the decisions, it's like big O of, let me type it out, big O of 2 to the n, where n is the number of, where is it? N would be the number of levels in the tree, right? So if we had 8 levels in the tree, or 8, then the 2 would just keep duplicating over and over again, right? In the first node, you have 2 decisions, then you'd have 4 decisions, then 8 decisions. So that would be O of 2 to the n there. So in this case, the number of levels in our recursion is, or the depth of our recursion is going to be the length of the word. So, and there's 3 decisions, so it's 3 to the L. And we multiply it by n because we're calling this DFS call at most n times for the entire board, right? Okay, so hopefully I've broken that down enough. And then space complexity would just be O of 1, because we didn't create any, we created some constant space here, but yeah, again, it's constant, and we reused the board for the visited. So we didn't create any extra space, so O of 1. Cool. So if you like the video, you can give it a thumbs up. And if you want to subscribe, you can. Cool. Bye.